Welcome to Koala Reading Historic AI, your gateway to the groundbreaking world of artificial intelligence. Join me, your host, and the voice behind the text-to-speech model as we explore landmark papers in deep learning that have shaped the course of AI history. Each episode, we will explore the papers that revolutionized this episode's field, and I strongly recommend delving into these papers as their significance is unparalleled. Let's embark on an unforgettable journey into the realm of AI. In today's episode, we will talk about important papers in the subject of computer vision to discuss. Let's begin with a brief overview of each one. 1. AlexNet, 2012. ImageNet classification with deep convolutional neural networks. This seminal paper introduced the AlexNet architecture, a deep convolutional neural network that revolutionized image classification by winning the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, in 2012. Its success marked a turning point in the dominance of deep learning in computer vision tasks. 2. GANs, 2014. Generative Adversarial Networks. This paper proposed Generative Adversarial Networks, GANs, a framework for training generative models through an adversarial process. GANs have had a profound impact on the field of AI, enabling the generation of realistic images, videos, and other creative content. 3. ResNet, 2015, Deep Residual Learning for Image Recognition. The ResNet paper introduced residual networks, which allowed the successful training of extremely deep neural networks. ResNet's skip connections mitigated the vanishing gradient problem, enabling the construction of deeper networks with improved performance. Now that we have an overview of these exciting papers, let's take a deep dive into each one. We'll explore the abstract, methodology, and the changes this paper made in its field. 1. AlexNet, 2012. ImageNet classification with deep convolutional neural networks. Abstract. The ImageNet classification with deep convolutional neural networks paper, authored by Alex Krzyzewski, Ilya Sutskever, and Jeffrey E. Hinton, introduced the now famous AlexNet architecture, which revolutionized the field of computer vision and deep learning. Published in 2012, this landmark paper presented a breakthrough in image classification accuracy and played a pivotal role in propelling the dominance of deep learning in various AI tasks. Methodology. AlexNet was designed as a deep convolutional neural network, CNN, with 8 layers, making it significantly deeper than previous architectures. The network's structure featured 5 convolutional layers, interspersed with 3 max pooling layers, and concluded with 3 fully connected layers. A unique aspect of AlexNet's design was the utilization of the ReLU, Rectified Linear Unit Activation function, which addressed the vanishing gradient problem and accelerated training. Furthermore, the authors employed dropout regularization during training to reduce overfitting, leading to improved generalization capabilities. To train the network, the authors utilized a large-scale dataset called ImageNet, which consisted of over 1 million labeled images spanning 1,000 different object categories. Notably, they employed graphics processing units, GPUs, to accelerate the training process, significantly reducing the time required to converge to a good solution. Changes in the field. The impact of the AlexNet paper on the field of computer vision and deep learning was monumental. Several key changes and contributions set AlexNet apart. Performance leap. AlexNet achieved a top 5 error rate of 15.3% in the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, 2012, significantly outperforming traditional computer vision approaches. This 8% improvement over the second-place method showcased the potential of deep learning and CNNs in particular for image classification tasks. Deep architectures. AlexNet demonstrated the effectiveness of deep neural networks, paving the way for researchers to explore even deeper architectures in subsequent years. The paper's success shattered the belief that shallow networks were sufficient for image recognition tasks. GPU acceleration. The author's use of GPUs for training was groundbreaking. It revealed the immense computational power of GPUs, highlighting their significance in accelerating the training of large neural networks and opening up new avenues for further research. ReLU activation. The adoption of the ReLU activation function in AlexNet played a critical role in addressing the vanishing gradient problem. ReLU's efficiency and non-saturating nature improved the network's training speed and overall performance. Convolutional neural networks dominance. AlexNet's triumph in ILSVRC 2012 shifted the research focus towards CNNs, leading to a surge in research and developments within the deep learning community. CNNs became the cornerstone of modern computer vision systems. In conclusion, the AlexNet paper's introduction of the eponymous architecture, coupled with its use of deep learning techniques and GPU acceleration, propelled the field of computer vision and deep learning into a new era. Its influence has been profound, inspiring countless researchers and shaping the landscape of AI research and applications to this day. 2. GANs, 2014, Generative Adversarial Networks. Abstract, the seminal paper, Generative Adversarial Networks introduced a groundbreaking deep learning framework authored by Ian J. Goodfellow, Jean Puget Abadi, Mehdi Mirza, Bing Xu, David Ward Farley, Sherjil Ozair, Aaron Corville, and Yoshua Bengio in 2014. The GAN framework comprises two neural networks, a generator and a discriminator, engaged in a captivating adversarial game. This innovative approach demonstrated unparalleled capabilities in generating realistic data samples, impacting various AI fields like computer vision, natural language processing, and art generation. Methodology. The authors proposed a two-player adversarial game in which the generator and the discriminator play opposing roles. The generator aims to fabricate data samples that are indistinguishable from real data, while the discriminator endeavors to differentiate between real and generated samples accurately. The generator is trained to transform random noise into data samples, effectively learning the underlying data distribution. Meanwhile, the discriminator is trained to distinguish between real and generated data, becoming increasingly proficient over time. Through this adversarial process, both networks iteratively improve, leading to the generation of remarkably realistic samples by the generator. To formalize the adversarial game, the authors introduced a novel loss function. The generator seeks to minimize the log likelihood of the discriminator making a correct prediction, while the discriminator aims to maximize the probability of correctly classifying real and generated samples. The competition between these networks facilitates the discovery of a Nash equilibrium, where the generator produces data samples indistinguishable from real data, and the discriminator can no longer differentiate between the two. Changes in the field. The introduction of GANs revolutionized various aspects of AI research and applications. Realistic data generation. GANs demonstrated unparalleled prowess in generating realistic data samples, including images, audio, and text. This opened up new possibilities in data augmentation, data synthesis, and creative content generation. Art generation. GANs led to the emergence of style transfer techniques, enabling the transformation of images into artistic styles. These methods have been widely used in art creation and digital content generation. Semi-supervised learning. GANs also showcased potential in semi-supervised learning scenarios where limited labeled data can be leveraged alongside generated data to enhance model performance. Unsupervised learning. GANs contributed to advancing unsupervised learning methods as the generator learns from unlabeled data without relying on explicit labels. Adversarial robustness. The study of GANs shed light on adversarial attacks and defenses, as adversarial perturbations could disrupt the generative process, leading to increased robustness considerations in deep learning models. In conclusion, the Generative Adversarial Networks paper introduced a transformative, deep learning framework that has had a profound impact on various AI fields. The adversarial game between the generator and discriminator set the stage for realistic data generation, art creation, and advancements in unsupervised and semi-supervised learning. The GAN framework continues to inspire cutting-edge research and innovative applications across the AI landscape. 3. ResNet 2015, Deep Residual Learning for Image Recognition. Abstract, the paper Deep Residual Learning for Image Recognition, authored by Kaiming He, Xiangyu Zhang, Xiaoqing Ren, and John Sun in 2015, presented the revolutionary ResNet architecture. ResNet addressed the challenge of training extremely deep neural networks by introducing residual connections, or skip connections. These skip connections enabled the training of networks with over 100 layers, leading to unprecedented performance gains in image recognition tasks and solidifying deep learning as the dominant approach in computer vision. Methodology. ResNet's core innovation lies in the incorporation of residual blocks, allowing the network to learn residual functions instead of direct mappings. A residual block consists of 2 or more convolutional layers, and instead of simply learning the mapping from input to output, it learns the residual between the input and the output. This is achieved by introducing a skip connection that directly adds the input to the output of the block. Mathematically, if Hx denotes the mapping to be learned by a few stacked layers, the residual function, ResNet learns the residual fx equals sign h times x. The output of the residual block is then given by yx equals sign hx plus fx, effectively combining the original input x and the residual fx to produce the final output yx. To facilitate the training of extremely deep networks, ResNet adopted the use of batch normalization after each convolutional layer. Additionally, the authors employed bottleneck architectures in deeper layers to reduce computational complexity while maintaining expressive power. Changes in the field. The introduction of ResNet brought about significant advancements in deep learning and image recognition. Vanishing gradient. Mitigation. The incorporation of skip connections mitigated the vanishing gradient problem, enabling the successful training of networks with hundreds of layers. This breakthrough dispelled the previous belief that deeper networks were challenging to optimize. Depth scaling. ResNet demonstrated that deeper networks could achieve better performance, inspiring researchers to explore even more substantial depths. This led to the development of even deeper architectures with improved recognition accuracy. State-of-the-art performance. ResNet significantly improved image recognition accuracy on benchmark datasets like ImageNet, achieving top ranks in the ImageNet Large-Scale Visual Recognition Challenge, ILS-VRC, 2015. Transfer learning and fine-tuning. ResNet's ability to learn hierarchical features in a data-driven manner made it an ideal choice for transfer learning and fine-tuning tasks, where pre-trained ResNet models were adapted to different image recognition tasks with limited data. General applicability. The residual learning paradigm introduced in ResNet proved effective in various computer vision tasks, such as object detection, semantic segmentation, and image captioning. In conclusion, the Deep Residual Learning for Image Recognition paper introduced ResNet, a groundbreaking architecture that enabled the training of extraordinarily deep neural networks. The introduction of skip connections not only improved optimization, but also set a new standard for state-of-the-art performance in image recognition tasks. ResNet's impact extended beyond image recognition, shaping the development of various deep learning architectures and advancing the field of computer vision as a whole. Thank you for listening to Koala Reading Historic AI. Hope you had fun, and if it is the first time you heard about those papers, I suggest you to read it again.